So I will, in some sense, this course is very complementary to Mauro's this morning, in that he mentioned at some point that some people might be happy or unhappy with the definition he gave. I'm definitely on the unhappy camp, but I know that all these definitions are important, and the purpose of this school and the subsequent program at Paris is precisely so that people who speak different languages can talk together, because we are all, in fact, interested in the same mathematics. So the goal of the course is to work on the other side. I will start today with a quick review of classical deformation theory, and we will see how naturally derived homotopical methods come in. You can even say that the first homotopical and simplicial methods in infinitesimal deformation theory are actually older than myself. And hopefully organically we'll see how the two viewpoints come together. So first of all, some conventions. I'm an algebraic geometer, so I will work with schemes, and my schemes will be always of finite type over the complex numbers, and algebraic stacks, and these typically, or maybe sometimes locally, of finite type, and the same for algebraic stacks. And I will very often have smoothness assumptions. So our infinitesimal deformation theory has an algebraic side, but also a complex holomorphic side. And so often I will use that smooth schemes or complex smooth varieties will be the same as holomorphic manifolds. And by the same, of course, I don't mean that they are the same, but that in a number of cases, one can interpret the same result in two different contexts using Gaga principle. And yes, and in particular, consistently with this viewpoint, a point will always be a C-valued point. And this is not necessary, and it's just for the purpose of this lecture. So a lot of this works without, if you are in algebraic geometry, all of this works over spec Z or anything else. And it's just easier for me to stay over the complex numbers. And in particular, the category of affine schemes will be the dual to finitely generated complex algebras. And when I say complex algebras, I always mean commutative with 1. Okay. So what is, as I said before, doing derived deformation theory today, the aim is review classical infinitesimal deformation theory and see homotopy, simplicial, derived infinity happen. So it's not something that, for me, this is not something that comes out of somewhere, but it was in there all along. And in this, I actually strongly agree with Mauro that, in fact, these higher methods simplify and clarify infinitesimal deformation theory. And so let me actually introduce another piece of basic language. There will be the category art. This is for Artinian rings, and this will be local C algebras, which are finite dimensional as C vector spaces. So in other words, their correspondent inside the affine schemes is what is called, I usually call fat points. So schemes, affine schemes such that the reduced structure is a point. Remember, point is always a spec C. And in particular, a notion we are interested in is the notion of I will skip this part because I will not need the usual one sometimes. Semi-small extension is a surjection in art such that its kernel, let me call it I, satisfies MA tensor I is equal to 0. And if you have never seen this, let me give you an example. You can take A is C of t modulo t to the n plus 1, and B is C of t modulo t to the n, and the map is the map that sends t to t.
Sorry, what is MA?
This is a local algebra, and MA is the maximal ideal. This is supposed to be a small Gothic or math frac M, but I cannot draw it. So you will have to use a normal M. I apologize. Okay. So the idea is how are categories coming into the picture? And this is very non-complex holomorphic as a viewpoint. I will think of schemes as their functor of points. This is also, remember, very, very close already to what Mauro was doing. So they are functors which satisfy certain properties. And in particular, if I have such a scheme, if you have a scheme X, sometimes this is called the restriction of the Yoneda functor, and it's defined by these are dimorphisms. Okay. And in here, of course, I have the category art, because these are C algebras, and so their specs are affine schemes. And so we get an induced map, but now we notice that art has not only a final object, an initial object, which is C, because these are C algebras. All C algebras have a natural map from C, but also it has a final object, which is also C, which is given by the fact that for any A, you have a natural map. This is the structure map, and it turns out that this is an isomorphism. So you can put this inside the assumption, but it actually follows from everything else. Because in general, it would have to be a finite extension of C, but of course, C is algebraically closed. So this means that this functor restricted to art splits up into, so Hx, and in fact, any functor D splits as disjoint union over D of C over its points. And so in particular, we will typically work with one connected component. We will typically assume that the cardinality of D of C is 1. So this is the context. A deformation functor is such a functor with this property and more properties that ensure that this will work well. So what is the idea? The idea is, in principle, deformation functors can be used to study moduli spaces.
Why deformation?
Well, I will come to it exactly now. So, very good question. Thank you. The deformation functors are used in studying moduli spaces and moduli stacks. In fact, let me highlight that the more general definition of algebraic stacks we use is due to Artin, and it appears in 1974 in a paper which has titled Versal Deformations and Algebraic Stacks. So the two notions are related from the very beginning. And so the idea is that when we think of moduli spaces and stacks, in fact, what we do is, like here, we take, if you want to view schemes as their space, as their functor of points, you are naturally led to think of all functors, and then some things will be defined for arbitrary functors, and other things will be defined by a bit more special functors. And in particular, for schemes, this will all make sense. And the same is, for instance, let me discuss, if I want to make moduli, typically what I want to do is work with families. So, for instance, what is a family of projective schemes over a base B? It's just a proper, a projective flat morphism. Notice that in general I would have to explain which definition of projective I'm using, because there are plenty of it, but if I take B affine in the sense I've given, they all coincide. So I don't have to worry about that. And then, of course, there is the notion of pulling back such a family, so making a fiber product. And there is the notion of isomorphism of such families, which means, if I have two of them, an isomorphism is, of course, an isomorphism here, which commutes with the projection to the base. Similarly, if I have X and Y schemes, what is a family of morphisms? And this is just a morphism from X times B to Y, or equivalently, it's a morphism from X times B to Y times B over B. Okay, and we view this as a family of schemes parametrized by B, in that to every point I get a projective scheme. I view this as a family of maps parametrized by B, in that for any point I get a map. And so what if my base scheme is actually the spectrum of an Artin ring? Well, then, remember, I just told you that this is a final object. It means each of these has a unique reduced point, geometric point. And so if I fix what is a point what is a family over C, or spec C. This is just X, a projective variety or a scheme. And here over C, a point, this is just a map, f from X to Y. And so, for instance, I can now define the deformation factor of f from R to sets. And I can say that, well, what is it over A? This is defined to be the set of all Y such that they restrict to F over the only point. Or if you want, another way to say it is they are commutative diagrams and here so what I want, hopefully I find a nice color, is to extend it. So in this sense, I view this as deforming my map F infinitesimally at first order, second order. If you think of this as in the case where, for instance, A is a C of t modulo t to the n plus 1, it means I deform it to the first order, to the second order, and so on. But not infinitely, only until order n. And notice that on the other hand, when I take the deformations of X of A, and X is a projective scheme, so I've chosen a point. I've chosen a family over one point or a one point in the moduli. And then what I do is I define this as, well, the same thing, Cartesian diagrams. And this is projective. I don't really need projective here. Projective is automatic. All I need is flat. And here I have a choice. You see, here this is very big. And so I have to do, I can do two things. I can say up to isomorphism. And the isomorphism, of course, if I have two of these, it's an isomorphism that makes the diagram commute. Or I can take the whole groupoid. And by groupoid means I don't quotient by the isomorphisms. I just remember that I have these families, and these families have some isomorphism between them. So this means we are really working with a stack. This is how you do stacks. You take families, and instead of killing the isomorphisms, you honor them and recognize them. And this is sort of the traditional approach. And there is an immediate thing I want to point out, which is related to this. I told you, you don't need projective anymore. Once it's flat, you're good. Working infinitesimally allows you to drop assumptions. So typically, to get reasonable structure on a moduli of schemes, you typically want them projective, because otherwise, if you just have flatness, you can do strange things, like say you have a P1 times a basis, and then you remove 1 point from one of the fibers so that it becomes on A1. So you have a family, but the general fiber is P1, the special one is A1. This doesn't sound like a good thing to do. But infinitesimally, this problem does not exist, which means that working in this infinitesimal way allows us to study more general stuff, to study, for instance, all these problems without, for instance, here, to get a nice algebraic stack of maps, you typically want that x and y are projective. You can weaken it a bit to get it proper, but but you really want some assumptions so that you get an algebraic stack. But these computations don't really see these global properties. And of course, in particular, you can also work with the functor itself, and you can take for x a scheme and p a point of x, you can consider. And this is then the commutative diagrams or if you want, this after all is a C-value points. So it's the set of these maps such that this diagram commutes. In particular, I hope you all have seen that this one is naturally isomorphic to the tangent space of x at P. And this actually is this seemingly trivial remark is actually non-trivial. This will be a key fact in everything we do. Because you see, here, what do I mean by naturally? This is a set, and this is a vector space. So how do I mean that they are naturally the same? I have to kind of here build the structure of vector space. And the structure of vector space is, first of all, you want a 0. And the 0 is associated to this map. This, after all, gives you, if you want, it means you push back spec A onto spec C, you take the constant map, and you go back down. The scalar multiplication is associated to the fact that you have a map from this to itself, which is given by the multiplication via lambda. And so if you have such a thing and you compose with an automorphism of spec A, you get a different map. And then there is the addition, and I will not write this down because it takes a little bit longer. And notice that these two you can define for any functor, the 0 and the multiplication by scalar, because they come from properties of the category art. The multiplication by scalars is still defined in terms of art, but it requires an extra property, and I will not want to write this now. But the point is, you can completely recover the tangent space. And so, sorry, I did the bad thing. Somebody should have told me. No. Okay. This is too high. Okay. Okay, better. And this is T2. So this means that under some mild assumptions, we can always define tangent spaces to all these deformation problems. And in fact, they can be computed explicitly, and this is a very classical result, in a number of times, in a number of cases. So under mild assumptions, we can define T1D, the tangent space, to D any functor from, well, again, there are assumptions, and this is called the tangent space, and notice it has a 1. We will go back to this, why it's called 1, but let me give you examples. So for instance, of course, in particular, we have seen that T1 of hxp is Tpx. So this is a natural vector space structure on D of C epsilon mod epsilon squared. So this we have seen. So for instance, if I want to study def f is the one written up there. And then this is h0 of x pullback of ty if y is a smooth scheme. But it's not necessary that x, y are projective. So the other example I want to work with is what is T1 of deformations of x, and this is h1 of x tx if x is smooth, but again, not necessarily projective. Notice a difference, that here my T1 is actually a h0, and here is an h1. And this is exactly related to the fact that in the above case, there was no notion of two isomorphism. Either two maps are the same or they are not the same. But in the second case, there was a notion of isomorphism. And in fact, what you get is that h0 of x tx is the tangent space in the identity to the group of automorphisms of the trivial deformation of x over spec C. So if you want, you are working with a stack. It means you no longer have an underlying set. You have an underlying group point. So the objects are points with automorphism group. And what this person does is compute for you the tangent space in the identity, which is where you usually compute. Of course, the tangent space to a group is the same in every point. But conventionally, we pick the identity. And in particular, notice that, and this is often denoted by T0. And in this case, the T0 is 0. And notice that, therefore, from the viewpoint of deformation theory, the difference, the natural difference is not between schemes and stacks, but the difference is between schemes and the Lin-Mumford algebraic stacks and Artin algebraic stacks. And here this exactly means that the automorphism group of points R have zero-dimensional tangent space. And because we are on the complex numbers over C, this means that they are discrete. Notice that in general this is not true. So discrete or often finite if they are quasi-projective. But this is in general not true over the if K has characteristic P, K of T, the group of pth roots of 1, this is quite discrete. It's 1 point as a set, but it's not, it has a non-trivial tangent space because this is T minus 1 to the P. So notice that I'm sticking to my complex numbers, yeah? Okay, and
So here is in the first tangent is really the homology because you are working up to isomorphism.
yes.
And not
Yes, I really want to work up to isomorphism to have this defined. But it turns out that once you work only with tangent spaces, this working with up to isomorphism is fine. It's not a problem. You get, we will get in a moment to why what is, as I told you, traditionally we really work up to isomorphism, and here it's fine, and then I will see something else. So this means that we can compute the tangent spaces, and this is actually very useful because if you know the tangent space, and for other reason you know that it's a tangent space to a scheme, it means you can estimate the dimension of the scheme because it is at most the dimension of the tangent space. Yes?
Are you sure it's H1 of XTX, not HZ?
I am sure. No. I mean, there are many. You see, for instance, one thing you can check is that for P1, this is 0. You cannot, if you take curves of genus 0, there's only one. There's only P1. You don't expect to have a family of curves in which one fiber is P1 and the other fibers are something else. So this has to be 0. On the other hand, if you take H0 of TP1, this is 3-dimensional because this is the space. TP1 is O of 2, so the sections have 3 dimensions, and these are the automorphism of P1 or the Möbius I don't know, it's something I don't know how to say in English because I was taught in Italian, but it's something we used to call projectivities, or Möbius transformation, I think, might be more popular and has dimension 3.
But like you take the deformation of identity map, so this should coincide with this deformation of X. I mean, if you take the first notion of deformation,
Yes.
I take the deformation of identity map on X.
Yes.
So this should
Yes, you are correct. This is also the deformation. That's exactly what I get, right? Here. Oh yes, sorry, I forgot to say this. Thank you very much. So that you can notice that this is also the first order deformation of the identity, because if you start with the identity, any deformations will still be an automorphism. So doing the tangents to the automorphism or doing the tangent to the maps is the same. And so you get exactly the same thing, because if you pull back via the identity, you get the X. Okay, but then something special happens. And the something special is that now you can, and let me give you one more example because this might be useful in the future. So if F is a coherent sheaf over X, then you can study the deformations of F over A, and this is again FA. Okay, with an isomorphism of FA restricted to X times spec C with X, such that FA is a flat. And again, here we have exactly the same choice. We can work up to isomorphism, and of course an isomorphism is an isomorphism that commutes with this restriction map, or we can take the group point. If we want to do a stack, moduli stack of sheaves, we typically work with a group point. And in this case, again, we can compute T1 of def F, and this is H1 of the endomorphism of F if F is locally free. And of course, in this case, T0, which is H0 of end F. So this is just a Hom FF. And this is, of course, the tangent space to the automorphisms in the identity, because the automorphisms are open inside here, and this is a vector space. So it's its own tangent space. So we are exactly in the same situation. And now, lower than expected. And now, kind of a miracle occurs. And let me discuss the miracle. And the miracle is the notion of obstruction space. So let me go back to this notion of small extension, okay? So let me go back to a small or semi-small extension. Well, you can view it as spec B is closely embedded into spec A. And remember, doing deformations means doing a map to the moduli. Okay? So assume you have an element in D of B which you regard as a morphism from here to some moduli. And then, let me look, we have an induced map. Of course, this is a functor, so it goes like this. And this map is given by the fact that if you have a map from spec A to the moduli, of course, restriction induces a map from spec B to the moduli. And now we can ask ourselves the opposite question. Given a morphism from spec B to the moduli, does it have an extension to spec A? And if so, how unique is this extension? And so the first is an extension of the property of the tangent space is that we have an exact sequence T1D tensor I. This is tensor as complex vector space to dA to dB. So what does this even mean? This is an abelian group, but these are sets. So this is an exact sequence of groups and sets. And what it means is that this group acts on this set, and that two elements here have the same image, if and only if they are in the same orbit. And in fact, if we are in a case where T0 is 0, then we also have a 0 here, which means the action is fixed point free. And if T0 is non-zero, then we can precisely describe the kernel in terms of the automorphism functor. So it's kind of all computed by the system. But what is more interesting is that there exists an obstruction space T2 of D is a C vector space plus, for all small extension, a functorial, a set map dB to T2D tensor I functorial in an appropriate sense. It's what is a morphism of small extension is you stack two of them and you put vertical arrows such that diagrams commute. And you want that the morphism of algebras are algebra homomorphism and the morphism of vector spaces are vector C linear. And such that now this is exact. This is usually called obstruction, OB. This is not a tampon, it's a obstruction. And is exact. So you can see why it's called obstruction. You have a family over B, and to it you associate an element of this vector space. And it says that it comes from here even only if the image is 0. This is really how short exit sequences work. You take an element here, and to see if it's in the image, you check whether it goes to 0. And the first thing we can notice, by the way, here I told you we have an exit sequence of groups and sets. And what happens, more or less by definition, is that if A is a C epsilon mod epsilon squared, then this map is bijective, which means T1 is, after all, completely determined, and so is T0. But here it's clear that the obstruction space is not unique, because I can always replace T2D and put it inside something bigger vector space. All it sees is whether this is 0 or non-zero. If you ask yourself, how is this even a vector space and not just a pointed set, the answer is that the functoriality and the tensor, and this determines the vector space structure. And so now, the facts. If D is induced by a scheme or an algebraic stack by fixing one point, there always exists an essentially unique up to canonical isomorphism, just like the tangent space, minimal obstruction space. And in all moduli cases, T2 is obtained from, can be obtained, T2 is obtained from T1 by adding 1. So let me tell you what I mean by adding 1. It means that, for instance, I can take T2 for def f can be chosen to be as x pullback of Ty. Here I have an H0 and I put an H1. Or I have the T2 of def x is H2 of x Tx. Or I have that T2 of def f is H2 of end f. And finally, these moduli obstruction spaces are in general not minimal. But they are functorial. So what does it mean by functorial? That if there is a way to associate to a family a different family, then there will be, of course, an induced map. It's a map of functors, so it will induce the map on the tangent spaces or of moduli spaces, but also on the obstructions. So let me make an example. If f is locally free over x, say projective is not so important, then you have a map from the deformations of f to the deformations of the determinant, which is given by the determinant. If you want, you have a map from the moduli of vector bundles to the moduli of line bundles, given by the determinant. If x is projective, you can if x is smooth, you can extend this to any coherent sheaf by taking you take the determinant by constructing a resolution. And you get that this maps the obstructions to the obstructions. So that if you take a deformation of your bundle over spec B, and you check what is in H2 of endomorphism, the obstruction to extending it to spec A, this corresponds exactly to how you do it. Then you take the determinant, you get an element in H2 of O, because the endomorphism of a line bundle is O. But for a line bundle, you know that the Picard group is non-singular, and so this obstruction doesn't do anything. And so, in fact, the actual obstruction you can work with is the H2 of the traceless endomorphisms, and not all the endomorphisms. And if you ask yourself, what does this H2 of O do? Why is it there? Line bundles, Picard groups are smooth. Why is there a non-trivial obstruction? And here, you remember I told you I have my own reasons for working with the complex numbers. If the point is that you can view deforming a line bundle as just a problem over X. But I can also view it as a fiber of deforming the pair variety or scheme, comma, line bundle. And if my variety is complex, projective, and smooth, then my line bundle has a cohomology, first cohomology class, which is in H2, but is also in H11 in the Hodge decomposition. And so if I deform X, I mean, the class is integer, so there is only one way to bring it along, but it may not stay of type H11. It will, in general, get a component of, a component where in H2 of O. And the line bundle will extend if and only if the class stays of type 1, 1, if and only if this is 0. So basically, this is the situation in the classical situation. And as I've mentioned in his paper, Versal Deformations and Algebraic Stacks, Artin explicitly asked, can we make sense of this? And the answer is yes, we can. This is what we are all here for. This is what derived schemes do. They show what these abstraction spaces, these weird things that we get here are, and how we, why they have the properties which are listed here. Because they detect a subtler, a more general, I don't remember the word Mauro used, hidden, a structure that is there on the moduli, and we want to be able to understand it. In fact, using derived methods, you see here you can ask yourself, why stop at T2? I have H1, H2, I can go to H2, H3, you know, any number. What are their meanings? And the answer is, we can have a full answer using derived geometry. And what we will see is that, again, deformation theory has a very direct approach to this, which can, what you can most often do is you can, here you see we had a small high category contribution, but actually deformation theory was able to say a lot, even working up to isomorphism. And we will say something about that. In the meantime, however, I have still 5 minutes. So what I will do is mention how, remember, in my examples, I always have everything smooth. So, or my coherent sheaf is a vector space, a vector bundle. So, what if things are not smooth? And again, to this, the answer uses simplicial and homotopical methods and derived methods, and is the answer that I was saying is older than I am, or more or less the same. I was born more or less when Ilusy defended, I think after Ilusy defended his thesis, but between the publications of the 2 volumes of cotangent complex and deformation theory, which is, of course, one of the many nice books in French. So the idea is, what if I drop the assumption smooth, locally free, which you can view as a, both are expression of a freeness, okay? And the answer is, and this answer goes back to a number of people, which I will put just some names, but they are not the only names. And here, these are the PhD advisor when people worked as PhD students. And notice that missing names are due to me not having time or competence or memory, but not that this list is complete. But let me give you the version by Ilusy. And the version by Ilusy says that if you have f from x to y, a morphism of schemes, or local or ring, well, there is something like but I will not pronounce this and not use it. Then we can associate to it a complex in the derived category, and in our case it has coherent cohomology because my schemes have all these assumptions, but in general, of course, this is not true, but you have still quasi-coherent of X such that 1 H0 is canonically omega F, and 2 for any triangle we get, well, we all know from, hopefully, or many of us know, that we have such an exact sequence. This is an exact sequence of coherent sheaves on X, and this is induced by a distinguished triangle plus 1. So as usual in algebraic geometry, and also outside algebraic geometry, but I don't know about that, once you have a right exact sequence, you expect that it's the tail end of a long exact sequence, and this is exactly what happens. And if this is also true schemes and the Lim-Mumford algebraic stacks, and if it's Artin, then it's in degree up to 1 and not in degree up to 0, and I'm not going to discuss this. So in some sense, it means that this is the natural structure, and the way I find the tangent and obstructions is I assume everything is smooth and all the sheaves are locally free, and then I replace all the tangents by cotangents. This is usually easy by replacing cohomology with Hom. And then wherever I saw cotangent, I put the cotangent complex. And I replace coherent sheaves by their locally free resolution, assuming there is a finite one. And then I again use derived categories. And then I ask a friend to look it up in LUZ for me, because I cannot find things there. Okay, I think with this I should finish. Thank you so much.